Welcome. Okay, if you've got an operating systems exam coming up, you are in the right place. In this guide, we are going to break down the first 3 core units of OS to get you totally exam ready. We'll cover all the must-know concepts and even solve the numerical problems you're definitely going to see.
I mean, think about it for a second. How does your computer handle a game, a browser, and your music all at the same time without just freezing? Well, the answer is this powerful, invisible manager working behind the scenes. And that's your operating system, the real hero of everything you do on your computer.
So, here's our game plan. We'll start with the absolute basics, what an OS even is. Then, we'll get into how it juggles all your apps using processes and threads. After that, we dive into the really important stuff for your exams, CPU scheduling algorithms and memory management. And don't worry, we'll wrap it all up with a handy cheat sheet to make sure you're ready to go. All right, first up, Unit 1. Let's get right to the heart of it. What exactly is an operating system, and what is it doing for you every single second your device is on? The easiest way to think about the OS is as the executive manager of your computer. It's this super important layer of software that sits right between you and the physical hardware. Its job is to make sure all the different parts, the CPU, the memory, the drives, can talk to each other and work together smoothly. So every OS has these 5 core jobs. It handles process management, basically deciding which app gets the CPU's attention. It takes care of memory management, giving each program the workspace it needs. It does file management, creating all those folders and files you use. It manages all your devices, from your printer to your keyboard. And of course, security, which is huge. It protects your system from nasty stuff. Without these 5 things, your computer would just be a useless box of electronics. Okay, now that we know what the OS does, let's look at what it's actually managing. We're talking about the process. This is the fundamental unit of work where all the action really happens.
You see, a program just sitting on your hard drive is, well, it's just a bunch of instructions. It's passive. But the moment you double-click that icon, it springs to life and becomes a process. It's now an active thing with resources and a purpose. A great way to think about it is like a recipe. The written recipe is the program, but the person actively cooking in the kitchen, that's the process. It's the doing.
And every single process goes through this life cycle, these 5 states. It starts as new when it's being created. Then it goes into the ready state, basically lining up for its turn on the CPU. When it gets its turn, it's running. Sometimes it has to pause, maybe to wait for you to type something, and that's the waiting state. Finally, when it's all done, it's terminated. The OS handles all these changes without you ever noticing.
Now this is how modern apps feel so fast and responsive. A single-threaded process is pretty basic. It can only do one thing at a time. But a multi-threaded process, it's like having a whole team of workers, the threads, all working on the same project. One thread can be updating what you see on the screen, while another is saving your file in the background. It's all about doing multiple things at once, which makes everything feel so much smoother.
Okay, let's move on to Unit 2. So, you've got all these processes in the ready state, and they all want to use the CPU. How in the world does the OS decide who goes next? Well, that's the super important job of the CPU scheduler. And the key word there is strategy. This isn't just random. The OS has very specific goals. It wants to keep the CPU busy all the time, and it wants to minimize how long you, or your programs, have to wait. It's all about efficiency and fairness.
Let's start with the simplest strategy out there, first come, first served, or FCFS. It's exactly what it sounds like. Just like a line at the grocery store, the first process that shows up is the first one that gets to run. Here's a classic exam problem. Let's solve it. Okay, to figure this out, we draw what's called a Gantt chart. It's just a timeline for the CPU. So P1 arrives at time 0. It's first, so it runs for its whole burst time of 4 milliseconds. Our timeline goes from 0 to 4, with P1 running. Next, P2 arrived at time 1, but it has to wait till P1 is done. So P2 starts at time 4 and runs for 3 milliseconds, finishing at time 7. Then P3 starts at 7, finishes at 8, P4 starts at 8, finishes at 10, and last P5 starts at 10 and finishes at 15. Now for the waiting time. The formula is easy. Start time minus arrival time. For P1, it's 0 minus 0, so 0 waiting. For P2, it's 4 minus 1, which is 3. For P3, 7 minus 2 is 5. P4 is 8 minus 3, another 5. And P5 is 10 minus 4, which is 6. Add all those up. 0 plus 3 plus 5 plus 5 plus 6. That's 19. To get the average, just divide by our 5 processes. 19 divided by 5 gives us 3.8 milliseconds. Simple, but, as we'll see, not always the best.
All right, now for a smarter way. Shortest job first. or SJF. With this one, when the CPU is free, the OS looks at all the processes that are ready to go and picks the one that needs the least amount of time, the one that will finish the fastest.
And look at that, the average waiting time dropped. Let's see why. So P1 still starts at time 0 and finishes at 4. But now, at time 4, the OS looks at everyone who has arrived. P2, P3, P4, and P5. Who's the shortest? P3 with a tiny burst time of 1. So P3 gets to go next, running from 4 to 5. Now who's left? We pick the next shortest, which is P4. It runs from 5 to 7. Then P2 runs from 7 to 10. And finally, the big one, P5, gets its turn from 10 to 16. If you calculate the waiting times now and find the average, you get 3.2 milliseconds. This is a big improvement because it stops small, quick jobs from getting stuck behind long ones.
Last up is round robin, and this one is all about fairness. Every process gets a small slice of CPU time, which we call a quantum. In this case, it's 4 units. P1 starts at time 0 and runs for 4 units. It's not done yet, so it gets sent to the back of the line. Next up is P2. It runs from 4 to 8, and since its burst time was only 4, it's finished. Then P3 gets a turn for 4 units, and so on. It's like everyone gets a little bit of attention in a loop. This is what makes a system feel so responsive because no single program can hog the CPU for too long.
All right, let's jump into our final big topic, Unit 3, Memory Management. This is all about how the OS handles the computer's main workspace, the RAM. In this library analogy, it's perfect. The OS is the librarian. It has to know which shelves or memory locations are empty, where every single book or process is located, and how to make room for new books when they come in. It's a huge organizational task.
Now, this is one of the biggest problems for a memory manager: fragmentation, or wasted space. Internal fragmentation happens when you have a fixed-size slot and you put a small process in it. All that leftover space inside the slot is wasted. External fragmentation is different. It's when you have lots of little gaps between the processes. Added up, you might have enough free space, but because it's not all in one piece, you can't use it for a larger process.
So, how do we fix this? Modern systems use an absolutely brilliant trick called paging and virtual memory. The OS chops up processes into small, equal-sized pieces called pages, and it chops up the physical RAM into same-size slots called frames. This means a process doesn't need one big chunk of memory anymore. Its pages can be scattered all over the place, in any free frames. This totally gets rid of external fragmentation and even lets you run programs that are technically bigger than your RAM.
But, okay, what happens when your RAM is completely full and the CPU needs a page that's still on the disk? That's called a page fault. The OS has to pick a page currently in memory and kick it out to make room. But which one? That's where page replacement algorithms come into play.
And as you can see, the strategy you pick really matters. FIFO, first in, first out, is simple. It just kicks out the page that's been in there the longest. But that's not always a great idea, because that old page might be important. LRU, least recently used, is much smarter. It kicks out the page that hasn't been used in the longest time. This works way better, getting us much closer to the optimal algorithm, which is basically a perfect prediction of the future, something a real OS can't do.
Whew, we have covered a ton of ground, from processes to scheduling to memory. So let's bring it all home with a quick review of the most important things you absolutely need to know for your exam.
Seriously, if you can nail these 5 questions, you are in amazing shape for your exam. Make sure you practice them, especially the numerical problems. Go back and redo the examples we just did. The practice will make all the difference.
And that's a wrap on our operating systems crash course for Units 1, 2, and 3. Keep thinking about these concepts, especially that constant battle between being efficient and being fair. Now go ace that exam. Good luck!